Let's continue investigating an ancient example of modular arithmetic, which is related to the affine cipher. Previously, we defined a function f, which maps the day number to its corresponding luminary number. We noticed that this function has the same format as an affine cipher. We also found the inverse function, which maps the luminary number to the corresponding day number. So let's have a look at the function f. This is the format. We have a multiplicative constant multiplying the input variable, and then we have the addition of this additive constant. And then we compute the mod 7 operation. So 7 is the modulus. And we found this inverse function, which also has the same format. So for the function f, 3 is the multiplicative constant, and 4 is the additive constant. And for the inverse function, 5 is the multiplicative constant, and 1 is the additive constant. The modulus 7 is used for both the function f and its inverse. So this format is exactly what we would expect to see for the affine cipher. And this is an ancient example of modular arithmetic. Now, let's examine some very interesting properties that concern the additive inverses and multiplicative inverses mod 7. So we're using the prime number 7 as the modulus. 7 is a double Mersenne prime. So we can write it in this format. We have 2 to the power of 2 squared minus 1 in the exponent, and then we have minus 1 outside of the exponent. So in the exponent, we have 4 minus 1, which is 3. 3 is also a Mersenne prime. So we have a Mersenne prime in the exponent, and that gives us 2 to the power of 3. That is 2 cubed, which is 8. And then we subtract 1, and that gives us 7. So it's a very interesting property. 7 is a double Mersenne prime. And we can also write 7 as 2 squared plus 2 to the power of 1 plus 2 to the power of 0. So this is 4 plus 2 plus 1. And we can write this in binary. So 7 in binary is 1, 1, 1. Let's examine these 8 trigrams. So these 8 trigrams are notation from ancient China. And we can rewrite this ancient Chinese notation in modern binary notation. So observe that there are horizontal lines in this notation. When the horizontal line is unbroken, so you have a full horizontal line, we can interpret that as 1. And when there is a broken horizontal line, we can interpret that as 0. So these gaps indicate that we're dealing with 0. And by convention, we're going to read from bottom to top. So this value over here is 0, 0, 0. You can see 3 gaps. And this value is 1, 1, 1. You can see no gaps over here. These are all full horizontal lines. So these correspond to 0 and 7. And note that you can flip all of the individual bits, and you can get from 0 to 7, which is 1, 1, 1. And if you flip all of these, they become 0, 0, 0. So 0 and 7 are both ways that you can write the modulus. So both 0 and 7 are congruent mod 7, because they are both multiples of 7. Now let's examine these remaining 3 pairs of trigrams. So you can see that 1 and 6 are a pair. 1 plus 6 is 7. Or we can say that 1 and 6 are additive inverses mod 7. So observe that in binary, 1 can be written as 0, 0, 1. And if we flip each of these bits, then we get 1, 1, 0. And that is the additive inverse mod 7. And have a look at the trigrams. Here you can see a gap, another gap, and then a full line. So that can be interpreted as 0, 0, 1. And for 6, we have a full horizontal line, another full horizontal line, and then over here we have a gap. So that is 1, 1, 0. So 1 and 6 are examples of additive inverses. Now let's have a look at 2 and 5. 2 and 5 are also additive inverses. Now 2 can be written as 0, 1, 0. And 5 can be written as 1, 0, 1. You can see for 5, the gap is in the middle, but for 2, the gaps are on the outside over here, and the full line is in the middle. So you can flip each of these bits, and you can switch between 2 and 5. These are additive inverses mod 7. And then finally, we can see 3 and 4. So we can read this value over here for 3. This is 0, 1, 1. We have a gap at the bottom. But over here for 4, we can see there's a full line on the bottom and then these two gaps. So we can interpret that as 1, 0, 0. So again, if you flip these bits, you can switch between these additive inverses. So we can see that 1 and 6 are additive inverses, 2 and 5 are additive inverses, 3 and 4 are also additive inverses. When you sum them, you get 7. And 7 is the additive identity. So 7 is congruent to 0 mod 7. So that is some very interesting notation from ancient China, which we can rewrite using modern binary notation. So pay close attention to how these trigrams are arranged. So this is an analysis that describes the additive inverses. And you can see that when we were computing this inverse value over here, when we have -4, we saw that that is equivalent to 3. So 3 and 4 are additive inverses. So if you put a minus sign over here, that is notation for the additive inverse. So this -4 is equivalent to +3. And -3 is equivalent to +4. So finding the additive inverse of this additive constant is an essential step for finding the inverse function if you're dealing with an affine cipher. And another essential step is finding the multiplicative inverse. So now let's move on to the multiplicative inverses mod 7. And we're only going to focus on the non-zero values. So 0 is the additive identity, but 1 is the multiplicative identity. And 1 times 1 is 1, so that means that 1 is also its own inverse. And another value that is also its own inverse is 6, which is congruent to -1. So 1, you can get 1 by multiplying -1 by itself. So you can state that in this format over here. P minus 1, which is 6 in this case, if you square that, that is congruent to 1 mod P. Now, in other words, we can say that 6 squared is 36, which is 1 more than 35. And 35 is a multiple of 7. So that's another way of stating it. And every time you see this congruent sign, you can implicitly imagine mod P next to this over here. So the modulus is the prime number 7 for all of these examples. So we've identified that 1 is the multiplicative identity, and we've also identified that -1, or 6, is its own multiplicative inverse. Or in other words, 6 squared is congruent to 1 mod 7. Now, another interesting observation we can make is that if you take this value that is 1 less than the prime modulus, and then you find the factorial of that value, you will get that this is congruent to -1 mod P. Now, this observation is actually called Wilson's theorem. So Wilson's theorem states that P is a prime number if and only if P minus 1 factorial is congruent to -1 mod P. So that is Wilson's theorem. And we can see an example of Wilson's theorem over here. So 1 less than P is 6, and then 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. That is 720. And we can write 720 as 103 times 7 minus 1. So we have a multiple of 7 minus 1. and that is congruent to -1 mod 7. So implicitly, imagine that there is a mod 7 over here. Alternatively, we can also write this as 102 times 7 plus 6. And then we can say that this is congruent to 6. That's because -1 and 6 are congruent, mod 7. 6 is 1 less than the modulus. So we've seen this observation over here that is called Wilson's theorem. So we have analyzed 1, we have analyzed -1, or 6. That leaves 4 more values that we need to analyze. So these values are 2, 4, 3, and 5. Now we want to find the multiplicative inverses. We can use Fermat's little theorem to help us. So Fermat's little theorem states that a to the power of p minus 1 is congruent to 1 mod p. And a over here is a placeholder for these values, 2, 4, 3, and 5. So if we take these values and we raise them to the power of 6, which is 1 less than the modulus, then we will get 1 mod 7. So that means that if we go 1 power below, that is a to the power of 5, we're going to get the multiplicative inverse. So look at this relationship over here. If we take this value a and we multiply by a to the power of p minus 2, which for this example is 5, then we can condense that down and we can get a to the power of p minus 1. And Fermat's little theorem tells us that this is the multiplicative identity. So this is how we can find the multiplicative inverse. We compute the powers, and then when we get to a to the power of 5, we can identify that these are inverses. So we can see that 2 and 4 are multiplicative inverses. 4 and 2, again, they appear as pairs over here. And then 3 and 5 are multiplicative inverses. And then over here we can see 5 and 3. Now notice that when you take the multiplicative inverse, you're going to get a sequence of numbers that goes in reverse. So for the powers of 2, we can see 2, 4, 1, 2, 4, 1. So if we compute a to the power of 6, we're going to get 1 for all of these values. And what about for 4? Well, you get 4, 2, 1, 4, 2, 1. So it's just the reversed sequence. You can just read it in the opposite direction. What about for 3? For 3, you can see we have 3, 2, minus 1, 4, 5. And what about for 5? If we read in the opposite direction, we have 3, 2, minus 1, 4, 5. That's a very interesting observation. Now, pay close attention to these values of a cubed. Now, you can see that for 2 and 4, we get plus 1, and for 3 and 5, we get minus 1. Now, this observation brings us to Euler's criterion. Now, Euler's criterion can be stated in this format over here. This is a way of finding quadratic residues. So if we take a to the power of 1/2 of p minus 1, that is congruent to plus 1 mod p if we're dealing with quadratic residues. But if these a values are not quadratic residues, then we're going to get minus 1. So we have a criterion for identifying which of these a values are a quadratic residue. And here we have plus 1, so that indicates that 2 and 4 are indeed quadratic residues. Now, what does it actually mean for a value to be a quadratic residue? Observe that 2 appears over here for these a squared values. So 4 squared and 3 squared both give us 2. And observe that 4 appears here and here. So 2 squared and 5 squared both give us 4. So you can find values that square to give 2 and 4. That means these values are quadratic residues. Now, 3 and 5, they have these minus 1 values here, so they are not quadratic residues. And you can see that 3 and 5 do not show up in this a squared column. But just because they are not quadratic residues doesn't mean there's no interesting properties. In fact, 3 and 5 are both primitive roots. So that is a very special property. And observe that in this sequence of powers, you actually get all of the values that are non-zero. So you get 3, 2, minus 1 is the same as 6, then 4, 5, and then 1. So you cycle through all of the possible values if you see the powers of 3. And for the powers of 5, you just have to go in the reverse direction, and you're going to cycle through all possible values. Now let's have a look at this diagram over here. So this diagram allows us to see this cyclic pattern. It allows us to see that 3 is a primitive root mod 7. And another way we can describe 3 is that it is a generator of a cyclic group. It's a generator of a multiplicative group. So let's begin over here at the multiplicative identity, 1. If we multiply by 3, that gets us to 3 over here. If we multiply by 3 again, that's 3 squared, we are at 2. If we multiply by 3 again, then we have 6, which is congruent to -1. If we multiply by 3 again, that gives us this value 4. Now you can see that these are the same values that we saw in this column over here. So we have 4, and then we're going to get 5 over here. And after we multiply by 3, 6 times, we're back to 1. So this is another way of observing that we have Fermat's little theorem appearing here. So this is Fermat's little theorem. If you have a to the power of 6, you're going to get 1. And here we have 3 to the power of 6, and we have 1. Now, another way of stating Fermat's little theorem is that if we can multiply both sides by a, and that means that a to the power of p is congruent to a mod p. So implicitly, we have mod p over here. So if you have 3 to the power of 7, that gets you back to 3. So we can go 6 steps around this cycle, and then we go 1 extra step, that's 7 steps, and then we're back to 3 over here. So this is another way of stating Fermat's little theorem. And observe that if you consider the multiplicative inverse of 3, you can just swap the direction of the arrows. So you can start over here at the identity, and then you can go backwards. So you have 5, 4, 6, 2, 3, 1, and then 5. So if you go 7 steps around, you're back to 5. So this is what Fermat's little theorem is telling us. So if we go 6 steps around, then we're over here at the identity. And if we go 7 steps around, we are at that value a. So observe that 3 is telling us to go in the direction of the arrows, and 5 is telling us to go in the opposite direction. Now, there's another cycle that we can see here. We can see the powers of 2. So if we multiply 1 by 2, then we get over here to 2. And then 2 squared is 4. And then if we multiply by 2 again, we're back to 1. And we can again switch the direction of these arrows, and we can work out the powers of 4. So if we want to multiply by 4, we start off at 1. 1 times 4 gives us 4. And then 4 squared gives us 2. And then we multiply by 4 again, and then we have 1. So this is another interesting cycle. But observe that 2 and 4, they are not going to cycle through all of the values. So for these powers of 2 and 4, we only have a subsection over here. We only have a subset of all of the possible values. So that's why 2 and 4, they are not primitive roots. But 3 and 5, they cycle through all of the non-zero values. So they are generators for this multiplicative group. And we can describe both 3 and 5 as primitive roots mod 7. So that's a fascinating observation that we can see over here. And another interesting thing that we can identify is that these numbers above the arrows, we can call them indices. So we can say that this is the index over here. And another term that we can use is the discrete logarithm. So if we have 3 and we raise it to the power of 6, that gets us back over here to 1. So 3 to the power of 6 is 1. And another way of stating that is that 6 is the discrete logarithm, where 6 is the index. If we use this generator, 3, and we identify that index or discrete logarithm, then we can get back to 1 over here. So if we know the result and we know the generator, the value that is missing is the index or the discrete logarithm. And the discrete logarithm problem is very relevant in cryptography. So it's very nice to see a small example like this where you can see all of the values. But for practical examples in cryptography, the discrete logarithm problem is going to be defined over these really large groups that are defined with really large prime numbers. So you have to identify a generator for that group, and then it is very difficult to find these indices or discrete logarithms. And in fact, the computational hardness of the discrete logarithm problem is the basis of many cryptographic algorithms. So we've seen this visual depiction of these powers of these A values, 2, 4, 3, and 5. We have made some very interesting observations. We have made the observation of Wilson's theorem over here. We also observed Euler's criterion for identifying quadratic residues. We can see that 2 and 4 are quadratic residues. And we also identified the primitive roots, which we also called generators. So those are 3 and 5. And in this visual depiction, you can see that 3 goes over here, but 2 skips over 3. And you can also see that 3 squared is equivalent to 2. So this tells us that 2 is a quadratic residue, and 3 goes through all of the values, so it is a primitive root. So we saw this really fascinating structure that exists, and this allows us to compute both the multiplicative inverses and the additive inverses, and that allows us to find these inverse functions for this structure. And this format is exactly what we would expect to see if we were defining the affine cipher.